We're going to derive an expression for the inductance of a solenoid, which is a coil of wire, also known as an inductor, and consider the effect of a solenoid on a changing current. So if you put a solenoid in a circuit like this, what's the effect of this solenoid, this coil, this inductor there? So here I've got a circuit with a battery, a power supply, a resistor, and this sort of cylindrical coil of wire with N turns to it. Here's kind of a 3/4 view of it. If we look straight down on that same circuit, we've got this sort of big rectangular area here, and then our wire spirals through our coil. We're looking straight down the axis of the coil right there. Solenoid, coil, inductor, same thing. So I've identified two different areas here, the area of this rectangle that's relevant and the cross-sectional area of our solenoid. We care about those areas because we care about the magnetic fields that currents in these wires are going to be generating. If these wires are generating magnetic fields, then there's going to be magnetic flux through this area and magnetic flux through that area. So let's consider applying Faraday's law to our circuit here. We need a Faradian loop. So let's imagine starting here and just following our wire round, around, N times circling around, and then back to where we started. So there's our Faradian loop, and it is bounding an open surface, which includes the rectangular area here, and this cross-sectional circular area here, N times. Our loop is enclosing N of these areas, one for each turn of the coil. Okay, so the total flux through our Faradian loop, the total flux would be the sum of the flux through the rectangular area plus the flux through all N of these circular areas. So the total flux through the coil we represent like this, N times the flux through one turn of the coil. So that circle there is to indicate the circular cross-sectional area of our coil. So applying Faraday's law to this loop, going all the way around, the delta V is 0. We end up at the same V where we started. This term becomes our EMF minus IR, and then here is the rate of change of the total magnetic flux through the rectangular area and the N circular areas. So I'm going to split that rate of change of flux into these two terms, the rate of change of flux through the rectangular area and the rate of change of flux through the coil here. And once more, I'm going to replace this term with N times the flux through one turn. So this, our rate of change of the flux through the coil is N times the rate of change of the magnetic flux through one turn of the coil. Okay, so I want to consider the relative importance of these two terms. The flux that the current in this wire is generating through the big area and the flux that the current in the wire is generating inside our coil. So at points inside the big rectangle, we would have to try and compute the magnetic field strength by using the Biot-Savart law here, sort of breaking up our wire into an infinite number of infinitesimally short segments, ds's, and computing a challenging integral for each point. So the B field would be different in its different in its magnitude at all points inside here. We'd have a very non-uniform B field inside that area. Moreover, it would be relatively small. The current in this square loop, this rectangular loop, is going to be creating a B field here on the inside, pointing into the page, but it's not going to be very large, at least not compared to the magnetic field that we're going to be generating inside our coil over here, inside our solenoid. These N turns of current are going to be generating, as we've used Ampere's law to find in the past, a nice uniform B field given with a strength given by the Bunny equation here, and this will be a much larger magnetic field in here than we would have in our rectangular area out there. Therefore, what we're concluding here is that the magnetic flux through the rectangular area is going to be so much smaller than N times the magnetic flux through one turn here that it will be negligible in comparison. So yes, there will be some magnetic flux through this big area here, but it'll be so small compared to the strong flux we're getting multiplied by that factor of n inside our coil. So negligible, in fact, that in this equation here, we're always going to neglect the magnetic flux through all parts of our circuit except through a coil. Only the magnetic flux through a coil will ever be large enough to consider in our equations. So we'll drop this term altogether. We're going to neglect the magnetic flux through any region that's not a solenoid. And then our equation simplifies down to this. So we just have one self-induced EMF term to consider, and that's through the coil. So N times the rate of change of flux through one turn of the coil. Okay, our goal here is to get an expression for the inductance of our solenoids. Let's proceed with that. Here again is our solenoid. Let's give it some dimensions. Let's say that's cross-sectional area A, a height or a length here, we'll call it the height H, and the turn density, little n, is the number of turns, big N, divided by that height H. Let's simplify this expression for the self-induced EMF of our coil. Starting with the flux through one turn, well, we know our magnetic field inside an ideal solenoid is uniform. So our magnetic flux is just the strength of that uniform field times the cross-sectional area. And from the Bunny equation, we get mu naught Ni for the strength of the magnetic field. Okay, so that's our flux through any one single turn of the coil. Now our EMF will be the opposite of N times the rate of change of this flux here. So we want ddt of this expression. Mu naught, little n, and A are all constants with respect to time, so ddt just acts on that current I there. So this becomes minus big N times mu naught n di dt, and then A naught here. This isn't A naught, this is the area, the cross-sectional area of our cylindrical coil. Collecting constants here, I get minus this grouping of constants times di dt. We're showing that the self-induced EMF in the coil is indeed proportional to the rate of change of the current through the coil. And earlier, we defined this combination of constants as our inductance, L. So we've done it. We've got our expression for the inductance of our solenoid. Just going to rewrite that here. So here's sort of our conclusion. We've defined earlier the self-induced EMF of some object as minus a constant times di dt through that component of a circuit. So this is our proportionality constant, the inductance L. And now we've got an expression for the inductance of a solenoid. We see it only depends on these sort of geometric properties of the coil. The height of the coil, its cross-sectional area, A. So the coil, it does not necessarily have to be cylindrical here. It could be kind of like a square coil, and A would be that cross-sectional area of the square coil. That works just as well. So whatever the shape of your coil is, A is its cross-sectional area, there's its height, and then there N squared is the turn density. This is also known as that back EMF, that self-induced EMF, the back EMF from this coil. Did we see where that N squared came from? Let me make sure I hit on that. This was capital N there from the number of turns multiplying this rate of change of flux. But capital N is little n times H. There we go. So replace this capital N with the turn density times H to get this expression here, our final expression. Okay, there we go.